This here is a calculus problem that you'll see in which it asks you to calculate the volume of a figure with a certain number of constraints, 4 constraints in this case. And this problem tripped me up a lot when I first saw it. I didn't know what it meant to have, mostly I didn't know what it meant to have the cross sections perpendicular to the x-axis being squares. What does that even mean? First of all, what are these cross sections, and what is the consequence of having them as squares? And it really didn't make sense to me before I saw a picture of this. So I think drawing this out could really help us try to understand what this question is asking, what this figure it's talking about is, and then I think finding the volume of that figure will not be much trouble after that. So let's try to draw a figure here. Draw a graph of what this is. So let's go ahead here. Let's get our y-axis. Let's get ourselves an x-axis and a z-axis. Good, I've drawn my axes straight. I've done that so many times. Okay, so first of all, we have all of these 4 constraints here: y equals e to the negative x, the x-axis, y-axis, and the line x equals 1. These are the different constraints we have for the base of our solid, and the solid in this case meaning some kind of a 3-dimensional shape. And because it's talking about the base, the key insight in this part of it, in this part of the problem, is to realize this is just the projection here of this entire complicated 3-dimensional graph onto the xy plane. So we can redraw this one part of the problem onto the xy plane down here that I'm making, the xy plane, and we can figure out what the base of the solid will be, what the very bottom of the solid will be, and then we can worry about these cross sections that will give it volume that we can then go ahead and, not too hard actually, we can just go ahead and calculate it. So we have here 4 constraints. Let's do the easy ones first. We have the x-axis, so we know we're being constrained by the x-axis. We have the y-axis, so we know we're being constrained by the y-axis. Well, let's get a straight line now. And we have x equals 1. So let's say right here is x equals 1. We'll have this line right here. So we have this shape, and finally we have the curve y equals e to the negative x. Well, at x equals 0, this will equal 1, so let's just say this here is 1. And here we'll go down some exponential decay, and this region is the base of the solid. This is the base of the 3-dimensional shape we're going to calculate the area of. And remember, this is the base of it. This is just the projection of the shape onto the xy plane. So in reality, this base is also in the 3D graph, and we can draw it again there. Let's get our 4 constraints, the 3 easy ones. Here we have the y-axis, we have the x-axis, and we have the line x equals 1. And here, let's expand this out a little bit. Let's make it nice and big. So we have x equals 1. Now, we have the curve e to the negative x. Let's say this is where y equals 1. We have, again, some sense of exponential decay. And this here is just what we had on the two-dimensional xy graph. This is the same base of the solid S. And now we can move on to what really tripped me up, which was how the cross sections perpendicular to the x-axis are squares. What does it even mean to have a cross section perpendicular to the x-axis, first of all, much less why it would matter to be a square? Well, let's pick out a nice color here. I'll begin by illustrating it. Perpendicular to the x-axis here is the zy plane, this whole plane here. And you can see it has no x in it. I'll get rid of that now, though. And you see I drew it in a square, and that's important here. If we go, you see there's this distance here, 1 in this case, because we're where x equals 0. This distance is very important, because if the cross sections are squares, then the length of the square has to be the same as its height. So if I draw up a square cross section right here, square cross section from our base. Remember, this is on the two-dimensional graph, kind of like coming out of the paper. And if you imagine I'm high up now, I'm crossing across here, and then I go lower down and I come back. You can almost imagine that we're raising a sheet of paper from that point where it's just barely touching the y-axis, and it's going exactly the length it had to go on the y-axis up. And if we do that for another point, say here, we go slightly less up because, again, this is a square. We didn't have to go nearly so far to the right. And here I'll get in on filling in these squares here. If we go another point, here there's even less distance here. So we go, again, not quite so far up. And here at x equals 1, which is the shortest square, we barely have anything at all here. It's quite a small square. And if I were to connect up this figure here, you would see it gives some kind of a rough shape. And here I'll fill in, oh, this is not the color I was looking for. I can fill in the side, and I can fill in the top, and hopefully by now you're getting some kind of an idea for the figure we're dealing with. It's this kind of cone-shaped figure. And if we wanted to calculate the volume of this, we might say, okay, well, an integral would be useful. We're going to be somehow summing up an infinite number of things. What to sum up? Well, the problem is giving it to us right here. The cross-sections, these sheets of paper that we've been almost lifting out of the xy plane, these sheets of paper perfectly describe pieces of volume of this figure. And what is the area of the square? If we're going to be integrating over all of the areas, well, the area of the square, clearly, any of its side squared, right? Well, one of its sides is y equals e to the negative x. So if we say e to the negative x squared, this gives us the area of that square, one of these squares, given an x, one of the squares on our journey down, summing up infinitely many squares to form this volume. And of course, a square area won't do it on its own. We have to add dx, a tiny volume to that square, to make it a tiny, tiny rectangular prism. And now, of course, if we were to integrate this from 0 to 1, we'd be adding all of the infinitely many squares lifted up from the xy plane, all these tiny, infinitely small sheets of paper, summing them all up to get the volume of our figure. And this right here, this is not a terribly hard integral. Now let's just scroll down. I read the word square from the problem. Let's scroll down and solve this. And the first detail you might realize, if we just rewrite our integral here, is that e to the negative x squared is the same as e to the negative 2x. E to the negative 2x, and then of course dx, that tiny bit of volume. And if we rewrite this just one more time, we can get in square brackets going from 0 to 1, this antiderivative starting at 0, ending at 1. We have, well, what is the integral of e to the negative 2x? If we imagine using the chain rule on the derivative, the reverse chain rule, we get e to the negative 2x divided by negative 2. Because this expression, when we take the derivative of it, e to the negative 2x by the chain rule will be negative 2 times e to the negative 2x. And then the negative 2 will divide by the negative 2 that we are dividing by here, and it'll all cancel out. And if we can distribute out this, factor out this negative 1/2, we get that this will be negative 1/2 times, well, at 1, e to the negative 2x, remember the negative 2 we've just factored out, the e to the negative 2 times 1, e to the just negative 2, and then minus what this is at 0. But at 0, this is just e to the negative 2 times 0, and anything times 0 is 0, so this is just e to the 0, which anything to the 0 is just 1, is minus 1. And we could, if we really felt like it, we could rewrite this in one more way. Negative 1/2 times negative 1 is 1/2, and we could subtract e to the negative 2 times negative 1/2, which is, well, just the same as minus 1 over 2e to the 2, and the 2 is now positive instead of negative because we're dividing by it. Both of these are perfectly valid ways to write the answer to the question, what is the volume of the figure here defined by the constraints? And hopefully it makes sense to you now how this question is really just defining a base, defining some kind of a base for this figure to rest on, this shape, this, in this case, kind of tube shape, and it's defining that figure, and then you have little sheets of paper in squares being lifted from it. And before I end the video, I want to show you one other trick that problems like these are going to have, and it's instead of having the cross sections be squares, to have them instead be something like a semicircle. And I don't want to solve the problem if it was a semicircle, but just to give you a little intuition on what it would look like if it was a semicircle, instead of a square that we had coming out of the xy axis, let's redraw our graph one more time. Here we have the y-axis, here we have the z-axis, and here we have the x-axis. If we draw out our constraints again, remember the base is going to be exactly the same. We're going to have a y-axis constraint, an x-axis constraint, an x equals 1 constraint, and we're going to have our sense of exponential decay here. This base is no different from the base we had up top. The only change is what we're extending out of the xy plane. What type of paper you can think we're pulling out of it. Now, instead of, this is what we had last time where we pulled out a square. This is what we had last time, we pulled out a square. Instead of that, if we pull out a semicircle, instead of having a square, we just make a semicircle shape. We pull out almost like if you had cut a sheet of paper into half a circle and pulled it out. And you could do this in another place with a slightly smaller semicircle, and an even smaller semicircle, and quite a small semicircle. These semicircles are just being pulled out of the xy plane as if they're paper, and now you could form some kind of a region under these, and you could ask someone, hey, what is the volume of this region that I've just created by having these semicircles? Hopefully it makes sense that the cross section is just a means of creating volume out of this base that was defined by these constraints. And if you want a little bit of extra practice and you want some thinking using this intuition, you can try to think, how would I set up the integral? This is still the integral from 0 to 1 of something dx, but now what would I be integrating with? If my question to you is, what is the volume under this with a semicircle? You can maybe try to think about that.